In a previous video we were stating that if we have, for instance, a charge which we call positive and a charge which we call negative, well, there is an interaction between them. And previous knowledge, we know that if we have these two charges, they will attract each other. So there is a force that a positive charge is exerting over a negative charge, while there is a force that the negative charge is exerting over a positive charge, right? And this is an attraction. There is also, for instance, if we have charges of the same nature, there is repulsion, right? And we understand that the force that is going to be exerted here is given by a constant k. And this constant k, for instance, has a value of 8.99 times 10 to the 9. And these units, for instance, are Newton meter squared over Coulomb squared. And we have, for instance, Q1 times Q2 being Q1 or Q2. It could be, for instance, this could be Q1, this could be Q2, over the distance between both charges. So this is r, the distance between two charges squared, and we have a unit vector, which is what gives the direction of the force. And this force is generated by an electric field. So any given charge will have an electric field. If we have a positive charge, we state, this is mere convention once again, that its electric field will go towards the outside. So the electric field points towards the outside of the charge. This is mere convention once again. While if we have a negative charge, well, the electric field will have a direction towards the inside of this charge. Is it okay? And each charge will exert an electric field. For instance, the electric field is also a vector. It has direction, and it's the constant k times the charge we're analyzing over r squared times the unit vector. So if I want the electric field here, for instance, well, I will have in this situation probably here the electric field generated by the positive charge, and here towards this direction the electric field generated by the negative charge. Sorry, but in this case it will go towards the inside, which will move the vector towards this direction, and we can calculate the electric field in any given point, for instance point P, and it will have, for instance, well, a result, right? And we have, for instance, here R1, and here we have the distance R2, and we can actually obtain the sum of these two electric charges as a vectorial sum, and the total electric field is going to be given as the sum of electric fields given by each charge. If instead of having a lot of charges, for instance, discrete charges, for instance, we can count here, this is charge 1, this is charge 2. We have a continuous distribution of charge, and all of this, for instance, is a bar which is positively charged, and I want the electric field in this point. Well, I might actually understand that, for instance, this small part will actually generate a vector of electric charge here. This guy will actually generate one here, and if I go on, this guy will exert here. So this is a continuous distribution, and the electric charge for a continuous distribution is going to be equal to the sum of all the contributions. So if we have here a differential of the bar, a small piece of the bar, I have to add all these pieces, and this will make an integral. And we will have the constant k, we have the differential of charge over r squared, and we have the unit vector. So we will be talking about this kind of distributions in a later video.